In a previous video, we saw that when you place a current carrying wire inside a magnetic field, that magnetic field can push on that wire. It can put a force on that wire. In this video, we'll figure out the direction of this force acting on the wire. So how do we do this? Well, all we need to do is use Newton's third law. Newton's third law says every action has equal and opposite reaction. You see over here, the wire is pushing on the magnets. We can call that as action. Then the magnets push on the wire. We call that as the reaction. Because the action and reaction forces are opposite in direction, we will figure out in what direction the wire pushes on the magnets. And then in the opposite direction, the magnets will push on the wire. So let's first figure out in what direction the wire pushes on the magnets. Well, to do that, we'll ask ourselves, how does the wire push on the magnets? Well, the wire creates its own magnetic field because of the current, and it's that magnetic field that pushes on the magnets. So let's remove this magnetic field and concentrate on the magnetic field generated by the wire. We've seen before that the magnetic field due to a current carrying wire is in circles around it. And the direction is given by the right-hand thumb rule, where the thumb represents the direction of the current and the four fingers will represent the direction of the magnetic field. So the magnetic field runs like this. And just to recall, what do we mean by magnetic field direction is this way? It means that if I were to keep a tiny magnet over here, its north pole would experience a force to the right. If I keep a tiny magnet here behind the wire, its north pole would experience a force to the left. So the direction of the magnetic field tells us in what direction the north pole of any magnet kept over there would experience a force. Now, given this, can we figure out in what direction this magnet and this pole, these two poles will experience a force? So I want you to try to do this first, and then we'll do it together. All right, let's do this. To figure out the direction of the force on this pole of the magnet, let's just concentrate on the field at this point. Can you see that the arrow mark is pointing out of the screen? The field over here is pointing outwards. That means the north pole over there will experience a force outwards. And since I've kept our north pole over there, that north pole must experience a force outwards. So it's going to be somewhat this way. This way. All right. What about this pole of the magnet? Again, if you have not done this, now would be again great time to pause and see if you can do this pole yourself. All right, let's see. Over here, notice the arrow mark is pointing into the screen. It's a little difficult to see, but you have to understand that the field is running into the screen and then going behind the wire, comes out of the screen and comes in front of the wire. So since the arrow mark is pointing into the screen, this means a north pole over here would experience a force into the screen. But we have kept a south pole. South pole does the exact opposite thing of north pole, right? And so if the north pole experiences a force into the screen, the south pole would experience a force out of the screen. Oops. So the south pole would also experience, both the poles of the magnet experience a force out of the screen. And if this is a giant horseshoe magnet, like shown over here, then that means the whole magnet is experiencing a force out of the screen. So the wire is pushing the magnet out of the screen. And so from Newton's third law, this means the magnet must push the wire into the screen. So the force on the wire must be this way, into the screen. Again, it's a little difficult to see because drawing arrow marks into the screen is not all that easy, but just visualize this. And so that's how we can figure out the force on a current carrying wire placed in a magnetic field. Now I'm sure you agree with me that this is a pretty tedious method to first figure out the direction of the field generated by the wire, then find the force on the magnets, then use Newton's third law. This is too much work, right? Is there a shortcut to somehow just remember this? So what I mean is, if I go back to the original picture, so we figured out the hard way that if the magnetic field is to the right and the current is upwards, then the force on the wire is into the screen. So my question is, can we just remember this so that in the future we can solve problems very quickly rather than having to derive the whole thing again? Well, it turns out there is a way to remember this. And we can do that by using something called the Fleming's left-hand rule. So the Fleming's left-hand rule says you bring in your left hand and you stretch your thumb, forefinger, and middle finger such that they're all mutually perpendicular to each other. As you can see, these two are perpendicular, these two are also perpendicular, and even these two are perpendicular. Then the middle finger gives us the direction of the current. The forefinger gives us the direction of the magnetic field. Then the thumb gives us the direction of the force acting on that current carrying wire. All right, so force, magnetic field, and current. Now, for force, we use F. For magnetic field, we use B. The symbol for magnetic field is not M. Usually, we use B. And for current is I. So the way I remember this is FBI. Okay, FBI. So let's see whether it works in this example. In this example, our magnetic field is to the right. So this magnetic field, FBI, magnetic field is to the right. Our current is upwards. So this finger has to go up. Okay, there it is. So my current is up. And now notice the thumb is pointing downwards. That is, the force is into the screen. Exactly what we predicted from Newton's third law. But anymore, we don't have to use Newton's third law. We'll just use this Fleming's left-hand rule and do it. So let's do one more numeric. Let's take one more case. In this example, the magnetic field is coming out of the screen. It's not shown properly, but imagine the magnetic field is coming out of the screen. The current is to the right. So, can you use the left-hand rule to figure out what is the direction of the force acting on the wire? Try it yourself first. Pause the video and see if you can do it yourself. All right, let's do this. Bring in our left hand. Stretch it this way. FBI. So, F is the force, B is the magnetic field. Magnetic field is coming out of the screen. So magnetic field is coming out of the screen like this. The current is to the right. This way. Current is to the right, like this. I'm finding it a little hard to move my hands, so. And the thumb will give us the direction of the force. So the thumb, as you can see, is pointing downwards. Like this, in this direction. And so the force acting on the wire is downwards. Now, one last question we might have is, what if the magnetic field and the current are not perpendicular to each other, like as shown in the figure over here? What if there is some angle between the magnetic field and the current? What happens then? Well, it turns out the direction of the force won't change. The direction of the force will remain exactly the same regardless of what angle we have between the magnetic field and the current. So even if they're not at 90 degrees, we can still use the Fleming's left-hand rule. But always, the force will always be perpendicular to both these fingers. That's the thing. But these two need not be perpendicular to each other because it's our choice. We can keep the current carrying wire at any angle with respect to the magnetic fields. But don't worry too much about that. In most cases that we will be dealing, we'll always have them perpendicular to each other. But it's not a necessity. So what did we learn in this video? We saw that to calculate the direction of the force on a current carrying wire, kept in a magnetic field, we can either use Newton's third law, which is a little bit tedious, or we can use the Fleming's left-hand rule, in which the forefinger gives us the direction of the magnetic field, the thumb gives us the direction, the middle finger gives us the direction of the current, then the thumb gives us the direction of the force acting on the wire. And the way I like to remember it is force F, magnetic field B, current I, FBI.